A survey of a machine learning application in functional verification. Abstract. Functional verification, FV, the computational, and data intensive by nature, making a natural target of machine learning, ML, applications. This paper provides a comprehensive and up-to-date analysis of the FV problems addressed by, the functional verification problems addressed by ML. Among the various ML techniques and the algorithms, several emerging ones have demonstrated outstanding potential of functional verification. Despite of the promising research result, the paper identified critical challenges of applying the ML in the industry EMA environment. Finally, the authors indicate that the unavailability of high-quality verification data is impeding the result of ML in FV and calling for contribution to open verification datasets. Introduction. The ever-increased design complexity and the shortening design-to-market time has demanded faster and more accurate functional verification. Industry surveys indicate that design engineers spend about half of their time on functional verification. The situation has not improved over the years. By its name, FV functional verification is computation and data intensive, which makes it an ideal field to apply machine learning ML techniques in EDA. The ML development has witnessed exponential growth in the past decades. An abundance of the ML techniques has been devised to address challenges in the data analytics of the every data modality, including numbers, text, audio, image, video, graph, and the combinations of multiple modalities. Depending on the data, labels, availability, and the problems, nature, and supervised, unsupervised, semi-supervised, or reinforced learning can be applied to analyze the data. Many ML algorithms were also developed for these data analysis tasks, including regression and instance-based and regularization and distance tree and Bayesian and support vector machine artificial neural network (ANN), deep learning and dimensionality reduction, and many more emerging algorithms. Many ML algorithms had been experimented with different areas of the FE with various degrees of success. This paper contributed to the overall study of applying the ML to FE and by identifying problems addressable by ML, listing new techniques and algorithms that are applicable algorithms, outline the industrial perspective, and in discussing the challenges of data unavailability. Second, the topic of ML in functional verification. This paper outlined the important topics ML applies to in functional verification. Several existing publications have offered perspective on the general problem landscape. Huang, Guye, et al. Give a general overview of the ML application in EDA with limited coverage and verification about the test redundancy reduction and the test complexity reduction. Additionally, Ismail and Abdel Ghani provide insight into the automation of troubleshooting and automation of the formal engine selection, root cause analysis, and the environment modeling. In addition to the selected topics mentioned above, Christescu also present the topic of the automated code coverage. This paper gathers a comprehensive list of ML topics applicable to functional verification when including all functional verification topics in general perspective of programming code verification. Table 1 summarizes the topics and the subtopics and includes a column for related section, which follows the table. italicized text indicates the subtopics that were unexplored in other general survey publications. Table 1. Topics of ML application in functional verification. Topic: requirement and engineering, static code analysis, verification acceleration, coverage closure, and bug detection and localization. 1. Requirement engineering. Requirement engineering in functional verification is the process of defining, documenting, and maintaining verification requirement which is critical to ensure the excellent quality of the underlying IC design. 1.1 Requirement definition. Requirement definition involves translating ambiguous natural language NL verification objectives into verification specs with formality and precision. The quality of the translation directly dictates the correctness of the verification. Traditionally, this process is laborious and consumes substantial design cycles with several iterations of manual proofing to ensure quality. The two groups of classic approaches have been proposed to automate translation. One group of approach is to introduce constrained natural language (CNL). CNL is to formalize the specification drafting, followed by a template-based translation engine. This approach requires significant upfront investment in developing a powerful CNL syntax and a comprehensive compiler template system to ensure it is powerful enough to address most of the requirements encountered in functional verification. Furthermore, it burdens developers with learning an additional language which prevents the idea from becoming widely accepted. The other group leverages the classic natural language process (NLP) to parse NL natural language specifications and extract the relevant key elements to formulate formal specification represented in 10. The advance of ML translation in the NL domain has made fully automated machine translation commercially feasible and sometimes exceed the performance of average human translator. It's kindly the hope of the leveraging large-scale trained NL models with up to the billions of parameters to directly translate the NL specification to verification specs in system value assertion (SVA) and property specification language (PSL) or other languages. Several attempts to do a successful end-to-end translation have been observed, but none have been made product-ready. The major hurdle to this approach is scarcity of the available training datasets that pair NL specification with their formal translation. The most extensive datasets are merely about 100 sentence pairs. The number of pairs in comparison to their NL peers, which routinely comes in millions or even billions of sentence pairs. 1.2 Code summarization and translation to NL. Converse to requirement definition, summarization looks at the code and translates it into a human understandable NL summary. It assists developers in reading less ideally maintained code or understanding complex logic. An ideally implemented code summarization can insert inline documentation into code blocks or generate separate documentation. With its help, the maintainability and documentation of the code can be significantly improved. The application of ML on code summarization has been experimented with in more popular computer languages, for example, Python and JavaScript. So, several groups of approach have experimented with various degrees of success. The information retrieval (IR) based on approaches focus on applying the NLP to source code and looking for a similar code with existing summarization in place. This group of approaches heavily relies on the quality of existing code with the summarizes. Its use is only possible within a closed organization where many existing code repositories are readily available. Heuristic-based approaches instead try to define specific rules based on heuristics identified in a module definition. For example, a module with many submodules of this basic read and write command lines might be considered a memory module. Therefore, assembly can be constructed from the predefined pattern for the memory module. At the time of this writing, code summarization in IC design verification has not yet been reported in any literature. It is reasonable to be optimistic that the success of other languages can be realized in IC design and verification, which has not to be confirmed by the research community. In particular, recent regress of the cross-language models might help transfer learned knowledge from other programming languages to IC design. However, in addition to the challenges general to ML on code summarization, the intrinsic temporal parallelism in IC design and verification code can present challenges uncommon in other programming languages. 1.3 Specification mining. Specification mining, as described in Dahlmeier and Valentin et al., and Wenchao, Forin, and Sechia, has been a long-term software engineering topic. As an alternative to manually drafting the specification, it extracts specifications indirectly from the design under test duty execution. ML, machine learning, can be applied to mine recurring patterns from simulation traces. It can help automate either simulation-based coverage closure or formal verification. It is assumed that commonly recurring patterns might be expected behavior of the duty, and alternatively, an event pattern rarely occurs in the trace can be regarded as an abnormality. Therefore, it can be used for diagnostic and debugging purposes. ML has been applied to pattern discovery and abnormality detection across many designs where temporal data of a complex system are available. Azim et al. Propose a general software engineering approach where ML is used to discover formal specification from observing protocol traces and finding the possible pragmatical implementation of the protocol. Successful experiments cited in this paper have inspired the interesting follow-up research project in specification mining with ML. 2. Static code analysis. As the cost of fixing a bug grows exponentially along the stage of the IC developer, static code analysis offers an attractive option to improve the code quality and maintainability at an early stage of design development. 2.1 Code smell detection and quality assessment. Code smell refers to a suboptimal design patterns in source code, which might be syntactically and semantically correct, but violate best practice and can lead to a poor code maintainability. A particular example is code duplication, where the same function is implemented multiple times across the project or entire code here. So the code base. Some copies can have a particular bug fixed in a relatively short period, while the same bug goes unnoticed in other copies. The classical smell detection relies on defined heuristic rules to identify the patterns in source code. Instead of manually developing these rules and metric in the static code analysis tools, an ML-based approach can be trained on a large amount of available source code to identify code smells. Researchers detained by the Fontana et al. And Aniche et al. Has proven that smell detection with the ML can lead to universal code smell detection and significantly fewer patterns implementation effort. The resulting smell score can be used for code quality assessment and help developers improve product quality consistently. Furthermore, ML-based code refactoring might provide a helpful hints on improved code smell or even further some candidate changes. The application of ML in FV is not yet feasible, and the unavailability of large training datasets has prevented existing research from fully exploiting this solution potential. 2.2 is coding assistance. Developers working on IC can be most productive when the proper tools are provided. Simple code completion is a standard feature in the modern integrated development environment, IDE or IDE. However, more advanced techniques involved deep learning were proposed and are maturing quickly. It is now possible to train ANNs with billions of parameters from many large-scale open-source code repositories to give reasonable recommendations of code snippets from the developers, implementation, intent, or the context. The ML might also help IC developers stay productive with a semantic code search, which allows retrieving relevant code by NL queries. As code is usually full of various abbreviations and technical jargon, semantic searches can be more effective in finding relevant code snippets without correctly spelling the key variable, function, or module names. So while similar to the semantic search in many existing search engines, and semantic code search is able to help find abbreviated and highly technical code with a vague concept. The mean reciprocal length of the best model evaluated in 23 can already achieve usable scores over 70%. Although theoretically, the same ML techniques applied to other programming languages can be applied to IC design. No research has been published yet on coding assistance. Verification acceleration. The surveys in 1.2 indicate the functional verification is still the most time-consuming step in IC design, and functional and logic errors are still the most important cause of early spin. Any improvement in the speed of FV will significantly impact the quality and productivity of IC design. ML has been used for both formal and simulation-based verification for their acceleration. 3.1 Formal verification. Formal verification uses formal mathematics algorithms to improve correctness of design. Modern formal verification orchestration employs formal algorithms to target designs of different sizes and types, and complexities and experience and heuristics can help developers select the most appropriate algorithms from the library for specific problems. As a statistical method, ML cannot directly address formal verification problems. However, it has been proven to be very useful formal orchestration. With its prediction or computing resources and the probability of solving a problem, it is possible to schedule formal servers to best use these resources to shorten the verification time by the first scheduling the most promising servers with a lower compute resource consumption. The AdaBoost decision tree-based classifier can improve the ratio of the solving instances from the baseline of orchestration from 95% to 97%, within an average speedup of 1.85. The other experiment in 25 is able to predict resource requirements of formal verification with a 32% average error. It iteratively applies feature engineering to carefully select features from DUT, properties, and formal orchestration, or formal constraints, which are then used to train a multiple linear regression model for resource requirement prediction. 3.2 Simulation-based verification. Contrary to formal verification, simulation-based verification usually cannot ensure complete correctness in the design. Instead, the design is put under a test bench with a certain random or fixed pattern input stimuli applied, while the outputs are compared to the reference output to verify if the design behavior is respected. While similarly spread or bottle of the functional verification, simulation-based verification can also suffer from long verification times. It is not uncommon for verification of the complex design to take weeks to complete. A compromising idea being discussed and experimented with is the use of ML to model and predict the behavior of a complex system. The universal approximation theorem proved that a multiple layer perceptron MLP, or a feed-forward ANN, with at least one hidden layer, can approximate any continuous function with arbitrary accuracy, whereas normalized recurrent neural networks RNNs specified from the ANN are proved to approximate any dynamic system with memory. Advanced ML accelerator hardware has been possible that ANN can model the behaviors of some IC design modules to accelerate their simulations. Significant acceleration may be achieved depending on the capability of AI accelerators and the complexity of the ML models. 4. Test generation and coverage closure. Besides manually defined test pattern and standard techniques employed in simulation-based verification include random test generation and graph-based intelligence test bench automation. Due to the long-tail nature of the coverage closure, even a tiny efficiency improvement can easily result in a significantly reduced simulation time. Much research on the application of the ML to FV functional verification has focused on this area. The extensive ML studies have demonstrated they can do better the random test generation. Most research employs a black box model, assuming that DUT is a black box whose inputs can be controlled and outputs can be monitored. Optionally, some testing points can be observed. The research does not seek to understand the behavior of the DUT, Instead, the focus is spent on reducing unnecessary tests. They employ various ML techniques to learn from the historically input and output observation data, tune the random test generators, and eliminate tests are unlikely to be useful. In a recent development in 31, a reinforcement learning RL-based model is used to learn from DUT's output and predict the most probable test for a cache controller. When the reward given to the ML model is a FIFO depth, the experiments are able to learn from a historical result and hit the full target FIFO depth in several iterations, while the random test generation based approach is still struggling to hit more than one. However, the paper does not further experiment with how it performs for more complex design where the reward targets are not easily definable. Reference 28 introduces an ML architecture with much finer granularity where an ML model needs to be trained for every cover point. A ternary classifier is also employed to help decide if a test should be simulated and discarded and used to retrain a model further. Support vector machine (SVM), random forest, and deep neural network are all experimented on a CPU design. It is able to close 100% coverage with 3 or 5 times fewer tests. Further experiments on FSM and non-FSM design have demonstrated 69% and 72% reductions compared to the directed sequence generation. However, most of the results still suffer from the limitation of the statistical nature of ML. A more comprehensive review of the ML-based coverage-directed test generation (CDG) in 32 gives an overview of several ML models and their experimental results. Bayesian network, genetic algorithms, and genetic programming approaches, Markov model, data mining, and inductive logic programming are all experimented with various degrees of success. In all the approaches discussed, an ML model can make a prediction based on the learning from historical data it's been gathered, but the minimal capabilities to predict the future, that is, which test might be a more promising option for hitting a cover test target. This kind of information is not yet available. The best they can do is pick the tests that are most relevant to the historical test. A promising experiment conducted in 33 explored a different approach, where the DUT is regarded as a white box, and the code is analyzed and converted to a control data flow graph, CDFG. A gradient-based search on a trained graph neural network, GNN, is used to generate tests for a predefined test target. The experiment on IBEX V1, V2, and TPU achieved 74% and 73% and 90% accuracies at the coverage prediction when trained with 50% cover points. Several additional experiments also confirm that a gradient search method employed is insensitive to the GNN architecture. It is noted that due to the unavailability of training data, most of these ML approaches only learn from each design without exploring any prior knowledge from other similar designs. 5. Bug analysis. Bug analysis aims to identify the potential bug, localize the code blocks containing them, and give fix suggestions. The surveys want to find the verification of an IC spends roughly the same amount of time as it does in the design that the functional bugs contribute to about 50% of response for an ASIC design. Therefore, it's critically important that these bugs can be identified and fixed in the early functional verification stage. ML has been employed to help developers detect bugs in designs and find bugs faster. The three progressive problems need to be solved to speed up the bug hunting in functional verification, namely clustering of bugs by their root causes and classification of root causes and suggestion of fixes. Most research focuses on the first two, with no research result on the third one available yet. In search conducted in 34 is semi-structured simulation log files are used for bug analysis. It extracts 16 different features from metadata and message lines from log files of undisclosed design. The experiment on clustering achieved adjusted mutual information AMI of 0.543 with k-means and agglomerative clustering and 0.593 with DVCon, even after the feature dimensionality reduction. Far from ideal clustering with the AMI achieved 1.0. Various classification algorithms were also tested to determine their accuracy in solving problems. 2. All the algorithms, including random forest, support vector classification (SVC), decision tree, logistic regression, k-neighbors, and naive Bayes are compared to their power to predict root causes. The best score was achieved by the random forest with 90.7% prediction accuracy and 0.913 F1 scores. Lafell et al. Proposed to use labeled datasets from code and commit to train a gradient boosting model, where more than 100 features about authors, revisions, codes, and a project were tested until 36 were selected for the algorithms. The experiment showed how that it is possible to predict which commits are most likely to contain buggy code and potentially reduce manual bug hunting time significantly. However, due to the relative simplicity of the ML techniques adopted, they are not able to train ML models that can consider rich semantics in code or learn from historical bug fixed. Therefore, they cannot explain why and how the bugs occur, not suggest revising the code to eliminate the bugs automatically or semi-automatically. 3. Emerging ML techniques and models applicable to FV. 2. Functional verification. Significant breakthroughs in ML techniques and models and algorithms have been witnessed in recent years. Our paper found that very few of these emerging techniques are adopted by functional verification research. And we optimistically believe the great success will be possible once they are used to tackle challenging problems in functional verification. Transformer-based large-scale NL, natural language models with billions of parameters trained on the enormous amount of text corpus achieved near human or exceeding human level performance in various NL tasks. For example, question answering, machine translation, text classification, attractive summarization, and others. The application of these research results in code analysis has also demonstrated these models' great potential and versatility. It has been demonstrated that these models can truly ingest a large corpus of training data, structure the learned knowledge, and provide easy accessibility. This capability is instrumental in static code analysis, requirement engineering, and coding assistance for several popular programming languages. Given enough training data, it is reasonable to believe that these techniques can train ML models for various functional verification tasks. Until recently, it was hard to apply ML to graph data due to the complexity of their structure. Graph neural network GNN advances have promised to a new opportunity for functional verification. The research in 33 converts a design into a code and data flow graph, which is then further used to train a GNN to help predict coverage closure of a test. This kind of white box approach promises a previously unavailable insight into control and data flow in a design, which can generate directed tests to fill potential coverage holes. Graphs can represent rich relational, structural, and semantic information encountered in verification. The rich information from training an ML model on graphs can afford many new possible functional verification tasks. For example, bug hunting and coverage closure. Number 4. Urgency of a large-scale verification open datasets. Despite many encouraging research results on applying ML in functional verification, many challenges must be addressed to realize mature and large-scale success. Among them, the biggest challenge is the unavailability of training datasets. So due to the lack of large dataset, much research has been settled for relatively primitive ML techniques that demand only small training datasets with hundreds of samples. The simulation has prevented an advanced ML techniques and algorithms from being applied. Historically, IC designs are considered highly valued property of their respective owners. The design and the associated verification data, including the verification plan, simulation settings, assertions, regression result, simulation logs, coverage data, trace files, and the revisions and their commits are also carefully guarded by their owners. If that were not bad enough, an internal survey has indicated a typical ML project will spend up to 70% of the team's time on data preparation. It is also confirmed by the independent study that general data preparation, including data cleansing, reporting, and visualization, takes 75% of data professionals' time. This is the time they spend before any exploration of an original idea. So the unavailability of quality training data and expensive data preparation is substantial hurdle for any team to research ML4FB, and it impedes research advancement and prevents research community from learning from each other's success. After spending so much effort and time to create their own data for research, very few researchers are ready to share their code or ML models publicly, making their research results hard to repeat or verify by other researchers. Consequently, it seriously reduced the value of the ML research result. The standardization of a data format and active contribution to this kind of verification data sets by community will significantly accelerate the development of AI ML for functional verification, and Siemens is actively working with the different consortiums and partners to make this happen. If there is anything to learn from the ML in computer vision CV community, it is that abundance of training data helps boost the research significantly. Published in 2009, ImageNet now contains 14,197,122 images in 21,841 categories as of August 2022. Its availability has helped researchers invent unthinkably deep ML models and compete with a compatible basis, which directly contribute to the practical application of deep learning. Challenges hosted by ImageNet help build a healthy community where researchers can afford to focus on learning, inventing, and training their models instead of spending effort to curate a small private data set. According to 42, ImageNet has changed the thinking of the ML community from paying attention to models to paying attention to data, which consequently helps define how models are developed. The opportunity of functional verification also lies in such kind of open data set. Our search on GitHub, RISC-V, and open course conducted in May 2022 also indicated that limited design data and even fewer verification data are available in the public domain. The table below summarizes our search result. We estimated that there are about 10 billion lines of code and comments altogether. This scale is hardly comparable to billions of projects and billions of lines of source code in other popular programming languages. Even more, the verification-related data are very sparse. Even if it is possible to generate verification data from the set of source code, tremendous effort must be invested by individual research teams to decode and use the data effectively due to the lack of the published and agreed standards upon common data schemas. Making these data usable for ML tasks requires a substantial effort to eliminate those with restrictive licenses and those with simple forks, followed by further deep cleansing to ensure the quality and usability of the final dataset. The paper did not identify any announced activities to curate open source verification dataset and making the available to the public. Table 2. Number of open source projects hosted on GitHub, RISC-V, and OpenCourse. The 5. Industrial perspective. In addition to the scalability of the data, several other challenges must be addressed to ensure the successful application of ML in functional verification. Model generalization is one of the most prominent challenges in many ML research results. An ML model's generalization capabilities measures how easy it is applied to the model trained from the training data to the problems that are new problems had been seen before. A model trained on data from specific types of design, coding styles, certain project, or some niche types of the data might not perform well for other types of design, other coding styles, other project, on other types of data. The hard-to-generalize research result will only have limited value in an industrial production environment, as the cost of training and managing these models can easily negate the value they bring the solutions. Model scalability is another challenge in applying these research results in a production environment. A model might perform well for a relatively simple design. However, there is a guarantee it would work equally well when applied to the large-scale design with billions of RTL with code from multiple development teams spanning multiple continents. To benefit from these models, additional investment in further model compression, additional computing resources, for example, ML accelerators, or establishing ML ops, might be inevitable. The decision to investment in this effort must be balanced against the expected return from applying ML, which is not yet evident in many cases. The third challenge is related to data governance in ML application. In real-world application, the owner of the dataset used to train ML model, the functional verification tool developers and the tool user might belong to different organizations. In combination with the distribution of computing power and availability of MLOps expertise, they may jointly dictate the selection of the ML models. For example, a user who can diverge her data out of her organization has no ML infrastructure may not be able to use an ML model that requires much computing for the training on her data to achieve optimal performance. Alternatively, an FB tools developed with mature ML ops workflow, cloud infrastructure, and knowledge may be able to offer attractive FB tools hosted in the cloud with easily accessible RESTful APIs as a user may integrate it into their functional verification workflow. 6. Summary. Abundant data are available along with the design's life cycle. ML is one of the best tools to extract values from the data for functional verification. This paper has presented a comprehensive survey on how ML may help address almost every aspect of functional verification. These typical applications and their state-of-the-art achievements are then summarized and discussed. Despite diverse ML techniques applied, most research still employs primitive ML techniques and is restricted by the scale of the training data. It is not dissimilar to the early days of ML application in many advanced domains and promote that the ML application of functional verification are still in their early days. Many advanced techniques and models are yet to be applied to exploit ML's potential fully. Exploit ML's potential fully. Much semantic and relational and structural information has not yet been fully utilized in today's ML applications. Working experience and reviews of the many research results have indicated that application of the ML in FE cannot advance at a much faster pace without a substantial quality data set being made available. The paper calls for efforts to build more extensive data sets to train more complex big ML models. Such a data set will afford the ML community to make research results more compatible, repeatable, and credible. The paper also presented other critical challenges to be overcome to release the potential of the ML in FE and generalizability, scalability, and data governance as three main challenges that every industrial researcher has to consider applying ML in real-world production. Recognizing their implication will also help identify the suitable ML models applicable to many possible diverse use cases. The paper's authors are optimistic. The functional verification is intrinsically a data analytic problem, and machine learning ML is a powerful tool to extract value from the abundance of the functional verification data. We look forward to seeing more contributions from the community in the developing quality data sets, applying advanced ML techniques, and successfully adopting ML in functional verification tools. The reference. Thank you for your time. Today I read this paper, this DVCon2023 paper, a survey of machine learning applications in functional verification. Thank you again and see you next time.